Okay, so our next topic up, really cool paper popped up on Archive this week. A new ultra short period binary discovered. So for those that don't know, a binary star system. Most stars in the sky actually that you see are part of binaries. Basically, not just a single star like the sun, but two stars that are orbiting each other. They can be the same type, different types, and so that's extremely common. And so some of the most famous stars in the night sky that you'll know of actually are binaries. Like
Yeah.
the best one I can think of, the brightest star in the night sky, Sirius, is two stars. Sirius B, I think, is the bright one, and then there's a very small one that's right next to it.
It's the other way around. Sirius A
Is it the
is
other way
the
around? Okay.
A0. I think it's A0 star, and Sirius B is a white dwarf.
Yeah, sorry, other way around. Yeah, you're totally right.
Yeah.
And so basically how fast they orbit each other is of great interest. And it's been theoretically predicted that you can get some really low periods depending on how the binary was produced, basically, and what type of stars you have. And so there's been a new discovery of an ellipsoidal binary with a 20-minute period. So that means two stars, not necessarily like the sun, but like much bigger than the Earth. Actually, one of them is a white dwarf, so not that much bigger than the Earth. But two, stars are orbiting around each other in under 20 minutes, which is just
Oh,
completely bananas.
it's incredible. What is the primary star, the bright one? Do you know what spectral type it is?
Let's see. So the visible star. The visible star is being so the companion is a carbon oxygen white dwarf. It's invisible. The primary star is an AMCVN star.
AMCVN. So
Yeah.
AM is typically an A star that's magnetic.
Yeah.
CVN.
CVN is a Canum Venticorum.
Yeah, that's right.
Venaticorum.
Yeah,
It's a cataclysmic variable.
those cataclysmic variable as well. Well,
Yeah.
that's interesting. So if it is an A star, that the white dwarf must have been evolved. It must have evolved, right? Because stars are not born
Yeah.
as white dwarfs. So it's the
Yes.
leftover remnant of a higher mass star. So that probably means it could be a very high A star or a B star, which means the system itself could probably only be 100, 150 million years old, possibly less.
So
So it's a
relatively
very
very
young
young.
system. Yes, very young. And 20 minutes, I mean, again, most stars aren't born in such short periods. What ends up happening is they're formed at some distance, and their orbital period might be, who knows, a couple of days, maybe. A couple of days is still a short period, but they must have come together in orbital period over the lifetime of the binary, which
So
which
actually, this is an area that I know a bit about. So a fun fact, because a lot of people binaries are quite common, but binaries actually cannot form by themselves. So what I'm guessing happened with this one is you had a third star that got
yeah,
ejected,
yeah,
releasing the kinetic energy, which allowed the two stars to increase their potential energy, basically to compensate.
to
So
shrink.
they may not have drifted together. They may have just basically collapsed together after a third star was ejected.
Yeah, that's very very common. But what you can get is you can get what's called spin orbit coupling, and so essentially the spin of the stars themselves can couple gravitationally with the orbital period. And what they can do is they can actually interchange angular momentum. So the spin of the stars can borrow, quote unquote, angular momentum from the orbit of the stars. So the orbit shrinks, but the stars themselves spin up. And,
Whoa,
and so they could be rapidly rotating as their orbit is shrinking.
that's so cool.
Yeah. And don't forget, they're also, if it's an elliptical orbit, if it's circular, it happens, but it's harder to do, of course. But if it's elliptical, like an egg shape, if I do it this way, that means there must be periods in their orbit where they're actually quite close together and then farther away and then close together and then farther away. So as they come closer together, they can have this spin orbital coupling where they interchange angular momentum. So their period can get shorter and shorter.
Is the spin orbit coupling mechanism, is that like a tidal disruption?
Yeah, essentially, yep,
Okay,
yep.
that's so it would make sense that it's being magnified as they get very close together.
Oh yeah, no, absolutely. Of course, because of course, gravity, as you know, gravity is a sort of one over distance squared effect. So in fact, as the closer they get, the stronger that coupling becomes.
That is super cool. I love this binary star stuff, and the the systems are always so extreme. Like this star in particular, the white dwarf companion, it's about the mass of the sun, but it's 10 times smaller. And it has a surface temperature of 25,000 Kelvin, which is
Wow.
like absurd. I mean,
Yeah, so that's very hot. So that also suggests it's young, by the way, because obviously white dwarfs will cool, they'll radiatively cool as they age. So 25,000 Kelvin is quite hot. So I suspect this is of the order of 100 million years or less.
so if
Because
it's
it's
over
still
100 million years, then is it possible that we could spot the sacrificial the third star if on its way out? It can't have gone that far.
Yeah, that's a good point. That is a good point. It depends on the ejector on the ejection speed of the tertiary component, because it could have gone, and we don't know the direction in which it's gone off. But there could
Right.
be a very high proper motion star in the vicinity, which would be a good candidate for that third party star taking away all the angular momentum with it.
That's a really that would be really exciting if we found the star that pushed those two together.
Yeah, that's a good one. I suspect the authors have looked for that star, but if they haven't, it might be worth dropping them an email and saying, "Hey, have you thought of this?" You know,
That's a great idea. I didn't even look to see if the authors were anyone we knew. I think
yeah,
it's I
who are
think
the
it's
authors?
I don't, but it's a team from Beijing. Um, so I don't know any of them personally, although I do have some collaborators. Oh wait, oh my God, it might be a different Wencheng, but I do have a collaborator who does this and he does supernova remnant stuff too. There's maybe somebody in the global supernova project on this paper that I
Oh,
was like
that's interesting.
might be able to reach out to him.
Yeah, maybe make that
Yeah,
suggestion. Look for high proper motion object relatively nearby. Do you know
yeah.
how far away is the system?
Oh, that's a great question. I don't off the top of my head. Here. Why don't I share the paper and we can take a look real quick?
Yeah, throw
Um,
the paper. Maybe give me the star name. I can do a quick search.
okay. Uh, oh, this is a big one. So this guy, Wenchang, um, he is oh, and he's at Tel Aviv. I think this is the Wenchang Lee that I know. So that's super cool. We could reach out to him.
Yeah.
I've emailed with him in the past.
What's the
Um,
system name?
the system name, it's a long one. TMTS J052610. This
Uh, all right.
this whole beauty.
Yeah. All right. Well, after we finish, I'll actually have a look at this.
Sure. It's on my blog, and if you guys want to, if anyone's watching, you want to read it too, it's just jrfarrow.blog. The paper's linked there.
So maybe the question to ask, and maybe our viewers would think of this too, is who cares? Why would anybody want to study this kind of object?
Yep. It looks like it's a 8 kiloparsecs, by the way, from the
Oh,
Galactic
8
Center.
kiloparsecs? Holy cow.
From the Galactic Center.
Oh, I see. So where's it
Yeah.
relative to us? All right. Well, I'll figure out the distance.
So, yeah. So yeah. So
Well,
why is it important?
I think we are also 8 kiloparsecs from the galactic center.
So it's right at our orbit.
Yeah, it's actually, it's the moon. Interesting. So yeah, the question to really ask is why do astronomers, professional astronomers like us, why do we care about studying these kinds of objects?
That's a really good question. I think you'd actually have better insight into that than I would, since your stuff was more your research has been very related to this. You can definitely give a better answer than me on this one.
Yeah, I mean, I think we're good friends, you and I, but I wasn't trying to put you on the spot. I think it's
Oh
one of
no,
those
not at
things
all.
where, it's one of those things where I think I would want to know the answer to this. And I think there are two biggies. The first is it's clearly related to stellar evolution, because the white dwarf must have undergone some cataclysmic process, probably a supernova-like event, or at least a series of novae events. And so that in itself is interesting, with the fact that the AM star has, first of all, has survived, because one could argue it could have been either sort of disrupted in the orbit, or it could have absorbed an awful lot of the ejecta from the white dwarf's progenitor, the host star. And the other is just to try and understand orbital dynamics. And that's important for all kinds of reasons, because understanding how stars form, understanding how stars orbit each other gravitationally, has all kinds of implications for even our own sun, because we have an effect on the sun, the Earth does, But of course, Jupiter and Saturn are the two biggies in the solar system. While all the orbiting planets are dominated by the sun's gravitational field, we also cause the sun to wobble slightly in its orbit. And so understanding orbital dynamics of systems with very, very different masses and evolutionary status is actually really interesting from an astrophysics point of view, but it may help us understand our own solar system as well.
So is it our solar system it has a single star, whereas this is a binary. Is it possible our solar system had a binary companion in the past, or will capture one in the future?
So that is a really interesting question. That's a hard question to answer. The very fact we have a very stable solar system with most of the planets being coplanar, they're all on the same ecliptic plane, and relatively stable in their orbits, would suggest that probably there wasn't a binary companion. There doesn't seem to be any star in the that we can find that looks, so we're not in a very wide binary. So, if the sun's here and all the planets are here, there's some other star that is a member of the solar system, but way, way, way far away. We can't find any evidence of that, at least not substantial evidence. Could it do so in the future? I suppose the answer is yes. We could gravitationally come very close to another star system and capture that system. Or if it's a high mass star, we ourselves could be captured. And by captured, I mean gravitationally attracted to that star.
Well, we wouldn't be able to capture it outright. We'd have to run into two other stars first.
That's
Right?
probably true, or unless there was maybe like a giant molecular cloud like the Orion Nebula next door that could act as a mass proxy. But you're right. I think the idea you're getting at is the fact that if we're crossing each other, the sun and another star in space, even at relatively low velocities, we're probably going to go right past each other. Even though we may slow each other down, we're probably not going to have it. There's too much motion in the orbital motion in us and the captured star for us actually to capture each other. So I think you're right.
I don't think it's possible. Like in terms of the n-body problem, I don't think it's possible for two bodies to start separate and then drop into a stable orbit, orbiting each other stably.
Yeah, it's at least highly improbable.
Yeah.
You're right. You need a third party, and that could be another star or a star cluster or a giant molecular cloud, something that has substantial mass to help you drain some of that gravitational kinetic energy away. Yeah, that's a good observation.
I love seeing studies like this. They've got beautiful spectra. Oh my goodness.
Oh, that's beautiful. Yeah, you see all those deep valleys. They're all hydrogen absorption lines.
Wow. How come we don't see a ton of emission here?
Because these types of stars, although the AM suggests that there is some magnetic activity, but it's very low. Higher mass stars. Is this just the? Let me look at the temperatures. Hang on. Temperature. Oh, this is of the white dwarf, actually. See here it says 25,000 Kelvin. That's actually the white dwarf. Yeah, the Balmer series lines. So white dwarfs, while they themselves have magnetic fields, very strong magnetic fields sometimes, they don't have much of an atmosphere to actually produce these emission lines. And the AM star doesn't have much of a magnetic field either. And so emission lines are typically caused by very intense magnetic fields exciting the electrons in the outer atmospheres of these objects. So you typically don't see emission lines for these types of systems.
That's really interesting. And I'm used to supernova stuff where we get a ton of emission because you basically have like a glowing, expanding shell. It's so cool to see the spectra for other objects like this.
Yeah,
this is a good paper.
Is it? Yeah, just show me that again. Is this a real spectrum? Oh, it is. I think it is.
This is the blue solid lines are the model fit.
Ah, yes, indeed. So you see the Balmer series. These are hydrogen hydrogen absorption lines. It's interesting though.
Do you remember which transition the Balmer series is?
I was just thinking the exact same thing. I think it's is it 3-2 or 4-3? So
let's find out.
I think it's 4-3.
It's a 3-2.
Oh, 3 to
I
2.
think
Okay, next one
three
down.
to two
So
for
4
hydrogen alpha.
yeah, for hydrogen. Oh, yeah. Well, hydrogen alpha is
Yeah.
Lyman. That's right. That's
Yeah.
2 to 1. And what we're talking about here is if you have an atom and you have electrons orbiting it, say hydrogen, for instance, the very, very lowest orbital of electrons is called level 1. If it gets excited into the next level, that's called level 2. And so when that electron de-excites, it goes from 3 to 2. That would then emit what we call Lyman alpha, which is the first excited state of hydrogen. So Balmer is the next one down, and that is from 3 to 2. So if this is your hydrogen atom, there's the first orbital, there's the second, there's the third. It's an electron being excited from 2 into 3. And then when it de-excites, it releases energy. And that would be hydrogen alpha, which is this very far right absorption dip here. Yes, that one. And it's at 62.8 angstroms.
And then these are as you get the higher level transitions, right?
Correct,
3 to 2 and
correct.
then 4 to 3. Yeah.
No. So 3 to 2, 4
3 to
to
2 is this
2,
one.
5
4
to
to 2.
2.
Yeah.
First,
Yeah.
3 to 2, 4 to 2, 5 to 2, and so on,
Right.
all the way down to the break. Yeah. You're right. Very beautiful spectrum, and you can see how it's peaking.
So
it's peaking way down here in the blue, which suggests its temperature is very high. Which this model is 25,480 Kelvin. So very nice spectrum.
it's such a clear black body too, which is super nice.
Yeah, that's right.